Hey, we left off on page 74, but I want to reiterate theorem 5.1, which said that if we have F is holomorphic in G inside the complex plane, and gamma is this some positively orientated closed curve that's contractible to zero, and very nice, and W is inside of gamma, then we discovered that the derivative was associated with that integral, but the integral now, Z minus W, now had a square on it, which makes us think that this theorem that we did to prove this should be generalizable. Well, what's really neat here is, in fact, it can. And this is a very powerful theorem. Same sets of information here. It turns out that you can take any derivative of a holomorphic function at a point W inside of G, that its value is k factorial over 2 pi I, the integral of gamma f of z over z minus w, and this is a k plus 1 dz. Now, this has some serious implications. It simply says then f is infinitely differentiable. It also says that its partials and all of its higher orders are continuous. X or y. This is pretty crazy. It simply says that holomorphic functions are much nicer than what can happen in the real plane. And we're going to really exploit this. Now, because of this, there's actually many, many more integrals we can do. Let me demonstrate one. The integral over dz over z squared z minus 1. And let's pick some path containing the bad point 0 and the bad point 1. So let's take some circle. Let's center at 1/2 radius 3 and oriented it that way. And so there's our gamma. Now the question is, how should we do this problem? Well, partial fraction decomposition, that's not really fun. It's much easier to use the theorems that we have before. So now what we're going to do is we're going to cut this with gamma 1 and minus gamma 1. And so now this integral is over, and we'll call this the right, gamma right, and we'll call this gamma left. So to gamma right plus gamma 1 of dz over z squared z minus 1 plus the integral of now minus gamma 1 plus gamma left over dz over z squared z minus 1. So this integral has now become this integral plus this integral, which means that in each case we have one and only one pole or bad point on the inside. This one has this on the inside, so we write it and this one has the z squared on the inside, and so we write it, and this is gamma r plus gamma 1, and this is minus gamma 1 plus gamma l. So now each one of these is a integral that we know the answer to. This one is an integral that has the standard z minus w in the bottom, so its answer is 2 pi I, and then the top evaluated at the central point. And so this will be 1 over 1 squared. So there's the first value. Now the second integral here uses that formula that says we can evaluate the derivative when you have a square in the bottom which is kind of cool. And it still has the same 2 pi I there because the k factorial hasn't had a chance to cancel anything. So guess what? This one gets evaluated the same way. We plug in 0, and so we get 2 pi I, and we plug in a 0 there. Well, it turns out these are positive and negative each other. We get 0 here, but that's not relative. What's important here is the method by which the integration was done. Now, if we want to use bigger and more difficult problems, we can just throw higher and higher powers into the bottom, and we still do that very simple process. All right. Now, I'm going to start using our complex variables to prove things that are really neat. So let's begin back in the day when we talked about dominant terms. Suppose I gave you a polynomial f of x equals x to the 7th minus 8, x to the 5th minus 22, x to the 4th minus 6x plus 9. And all of you know that we refer to this as a 7th degree polynomial. In fact, its exterior shape is completely controlled by just this term. If it's plus in the front, it's going to curve up to the right. If it's minus plus in the front and it's odd, it's going to curve down. And this stuff just seems to control the things in between. This is the dominant term. Well, if it's dominant, how dominant is it? Well, I want you to notice that if we look at all of these coefficients over here and we take the largest, let's take the max of these a sub I equals 0 to degree minus 1. And in this case, we'll put in absolute values as well. We get 22. So I want you to notice, if I actually plug in 22, we have 22 to the 7th. And the worst that all of this can be is 6 of those 22s to the 5ths, with one of them, maybe all of them, having that multiplier in front, 22. And so it looks, this is dominating this because it has one more 22 than those. Now, unfortunately, if that had been an x to the 6th, there would have been 6 of these, and that 22's in front, and this could have been larger, but then we can pull a trick where we can use twice 22, and we can get this bigger than all of the rest. In fact, if you just look at the coefficients, you can quickly and easily determine an x in which this will be larger than everything else. That's what we mean by domination. Well, let's formalize this into a theorem that's useful. And so we're going to go do the complex form. So let P of z be a polynomial, and d is called its degree. What the first thing we're going to do with this polynomial is we're going to take and we're going to factor out a to the d, z to the d, and what's going to be left, and let me write this backwards. So the last term has a 1. The second to last term now has a to the d minus 1 over a to the d, and it's 1 power less, 1 over z, and it finally goes down to a to the 0 over a to the d, z to the d. So these are decreasing powers of z. So now I want to take the modulus of this. Times the modulus of all of that. Now, here's something that we know. We know, by having done limits, that the limit as z goes to infinity of this piece basically goes to 0 because they're all in the bottom. So the only surviving piece is that 1. So this term goes to 1. So let's use theory from limits. Since the limit as z goes to infinity, modulus of z goes to infinity, this one expression equals 1, we can find a large enough modulus so that, well, we might be a little bit over 1, or we might be a little under 1. Let's just make that term less than 2, but less than a half. One's in between there, that's close enough. So be it. Well, what's this mean? It means that the modulus of P of z, which is equal to the A of d, z to the d, times that term, which we now know this term is bounded between 2 and that term is bigger than 1/2. And we have discovered a very simple fact, and that's what I was demonstrating before. That the polynomial, after a large enough value of z, is basically associated with just the leading coefficient and the leading degree, z to the d. Now, why is this so powerful? It's just a simple fact. It simply says that you have a dominant term. Well, now I'm going to prove a very deep theorem, a theorem that is surprising and is absolutely false in the real plane. Page 77 says, let P of z be a non-constant complex polynomial. Let's assume that P of z fails to have a root, a 0. Thus, P of z is not 0 ever. Now, we have polynomials like that in the reals, x squared plus 1, x to the 4th plus 1, lots of. Let's assume that happens for the polynomials. Well, I am now going to observe that I know how to take the derivative of P of z. It exists. And since it's never 0, the P of z is never 0, then I can look at this function. This is a complex function. Never 0 in the bottom, and by our rules is differentiable. In other words, it's holomorphic. Ooh, so now we can apply Cauchy's integral theorem. So 1 over P of w is the integral of 2 pi I, 1 over P of z, that's my f of z here, over z minus 0 dz around any circle centered at the origin of radius r. Whatever function I put there that's holomorphic, and it doesn't have this 0, then this integral must be the evaluation of the function. Well, I've been talking about tools. I even had pictures of hammers. So I'm now going to say, well, what tools do I have that could look at this? Well, one of the tools that I have is called the ML theorem, maximum times the length. So let's take a look at the modulus of this. This will be equal to 1 over 2 pi, because the modulus of I is 1, times the modulus of an integral over a circle. But the integral is controlled by the ML theorem. The ML theorem says how long is this arc of this circle? Why, that arc is 2 pi r. And now we just need the max of 1 over pz on that circle. But we proved this. We know that P of z has this bound by its coefficient, and z to the d, and 1/2 its coefficient, z to the d. So now we'll solve this for 1 over z. So if we put this in there, we'll get 1 over 2a to the d, z to the d is less than 1 over p of z, which is less than 2 over a to the d, z to the d. So this is the same as this, and since they're positive, that's why the inequalities didn't reverse. Well, we know that this guy is going to be less than this on C, but that's the module of Z on a circle is its radius. So this is less than or equal to R A to the D, and here's the crazy thing, R to the D. And since this is a non-constant polynomial, D is bigger than 1, we have this fact. Now, that says this is less than or equal to this for any circle centered at the origin. So I can let R go to infinity, and what do we discover? We discover that this has to be 0. Now, which point would you like to do it at? Doesn't matter. Let's do it at 0. This is impossible. So, what we've discovered is that we have a polynomial which has an impossible value. That's very strange. What was the assumption? Our assumption is that P of Z fails to have a root. So what's our conclusion? A polynomial that is a non-constant complex polynomial always has a root in the complex plane when it's greater than a constant polynomial. In other words, all polynomials in the complex plane factor. Now use math induction. That proves that the complex polynomials completely factor in the complex plane. In other words, it is possible to write down any polynomial you like and this thing must factor. Now, this theorem doesn't tell us how to do it. It doesn't give us a formula to do it. It just simply says it must happen. And it can't happen in the reals. In fact, in the reals, if you take abstract algebra and you manage to reach Galois theory, you would discover that there is absolutely no way to factor every polynomial over the reals, that we don't have a method for doing that. Yet, in the complexes, it says it's completely doable, but we don't know how to do these numbers. So now let's exploit that little trick that I just did. I did a circle, and I applied it to an integral on that circle, and then I used a limit as r went to infinity, and that caused something cool to happen. So the fact that these homotopies exist between various circles, that this circle is homotopically equivalent to another circle, and that the functions are analytic inside of them, then we have a tool that is very powerful. So I'm going to show you the power of this tool. This tool is a method by which we can evaluate real integrals. So here is a numeric method to evaluate real integrals. Now, because I took a limit as r went to infinity, almost every single one of these problems is going to be infinite integrals. But there are tricks that can keep it finite and other pieces go to infinity. It's not exclusionary, but I'm going to do it in the infinite realm. So I'm going to compute Now, you actually know how to do this. This is the arctangent, and you know the arctangent to the right goes to pi halves and the left goes to minus pi halves. So you already know from Calc 2 that your answer is going to be pi in your world of infinite integrals. But we're going to do it in a very different way. Instead, we're going to do something called lifting. We're going to lift the problem into a bigger and a harder world. We're going to do an integral of 1 over z squared plus 1 dz in the complex plane. We're lifted ourselves. We made the problem in a greater context, in a greater difficulty. Now, in order for me to be able to do this integral, I need a piece of my integral to reflect that. So I'm going to demonstrate that in the complex plane, there are many paths that contain part of the real line. So I am going to take a half circle who sits centered on the real axis from minus r to r on its diameter and then goes up at radius r. This is going to be my gamma, and here's going to be the direction. Now, why have I picked this one? Well, the answer is this little sucker here has one single bad value sitting in its middle, right here, I. Now, down here is minus I, but it's not inside of gamma. So what do we have going for us? Well, let's draw a little picture of this. We have gamma, we have I, and we have the integral around gamma, 1 over z plus I, z minus I dz. Now I wrote it this way because I have factored z squared plus 1. Z squared plus 1 has I and minus I as a root, and I put the z at the bottom. Now, I know that 1 over z, whoops, I know that 1 over z plus I is holomorphic in this region. I'm away from its bad point. And I is inside of my gamma. And so we know that this integral is equivalent to the integral around the circle, which we know its exact value. What's that exact value? Why, it's okay, so we're doing this integral, and by writing it this way, we know the answer is going to be pi. Why? Well, first off, this is our gamma. This is our f of z in the top, which is holomorphic in this region, which means that this gamma is homotopic to a circle centered around I. That means the I is in the bottom, so we apply Cauchy's integral theorem, and we simply have to evaluate the top function at I times 2 pi I. And that's where the pi comes from. It is 2 pi I times 1 over I plus I, which gives us our pi. So Cauchy's integral theorem applied to this path homotopically to the circle centered around I produces pi. But now I'm going to write it a different way. Here's the gamma top, and here's the gamma real. And so this is going to be the integral from minus r to r over dx over x squared plus 1, because when z is on the real line, it's real. So that's the integral of gamma real, plus the integral over gamma top of 1 over z squared plus 1 dz. But now, what's really interesting about this is I'm going to look at just this integral, and I'm going to use the ML relationship. Now, the ML relationship isn't deep. It simply says that I need to bound that function and know the arc length. Well, the arc length is really easy. It's half of a circle. So I'll have pi r, and now I just have to bound this function on gamma of 1 over z squared plus 1. But let's do the following. Z squared plus 1. We know that this is going to be less than or equal to z squared plus 1, but it's going to be greater than equal to z squared minus 1. And so now we invert these directions and we get 1 over z squared plus 1 will be less than or equal to 1 over z squared minus 1. But now we're going to say, we remember z is on gamma. Gamma is a circle of radius r. So on gamma says this equals 1 over r squared minus 1. this integral is less than or equal to this for every value of r. Well, we know this goes to 0. So by taking the limit as r goes to infinity, we know this number must be 0. So we've just shown that our unique integral, as we take the limit as r goes to infinity, that in order for that to go away, we have to get pi. So we've just done a real integral. This is a kind of a cool tool here. This tool is pretty powerful. All right. So time to go back to something that we looked at earlier, because we was mentioned because it has importance. So recall that if we have a domain inside of the complex numbers and we have a function from this domain to the reals, it's called harmonic if and only if mu of xx plus mu of yy equals 0. Now, we saw these harmonic things. They came about from the Cauchy-Riemann equations, actually, as part of your homework. So let's recall the Cauchy-Riemann equation. Let f be holomorphic in G inside of the complex plane. Therefore, f satisfies Cauchy-Riemann equations. This is exciting. What do the Cauchy-Riemann equations say? Well, they say the derivative of f is the partial of f with respect to x, which happens to be the same as minus the partial of f with respect to y, which says that if you write f of z as a mu plus a nu I, then f prime of z is mu of x plus I nu of x, but it's also going to be there's supposed to be an I there, minus I times mu of y plus I nu of y, which is nu of y minus I nu of y. Now, it says these things are equal, and so there's a couple of consequences. First, mu of x equals nu of y, and that nu of x is equal to minus mu of y. Now I'm going to continue with that. What does it say for mu of x to be equal to nu of y and minus nu of y to be equal to mu of x? Well, mu of xx is nu of xy, and minus mu of yy is nu of xy. Nu of xx equals minus nu of yy, which says nu of xx plus nu of yy equals 0. Holomorphic functions produce harmonic pieces. Now, I leave it to you to solve these equations the other way, but we also get nu of xx equals nu of yy. So there's a theorem here. When a function is holomorphic, then it's composed of two harmonic pieces. The nu and x are actually called harmonic conjugates when they create a holomorphic function. Now, it's time to think like a mathematician who's wondering about the things that exist in the world in such a way that other people may not know what's going on. Is it possible that this idea of harmonic is actually a direct consequence of holomorphic, and that's the only way they happen, that holomorphic and harmonic pieces are bound together? So could it be that harmonic pieces and holomorphic functions are like emeralds and topazes, or there are certain minerals that they come together? Why? Well, I think the example is something like this. In order to create topaz, the temperature must reach a very high temperature. And then the way it cools down, another fine mineral forms as the cooling down process. So topaz are formed in a situation with a higher temperature, but you must get rubies or emeralds or garnets on the way down, because in order to reach that higher temperature, there's lower temperatures on the way down. And so they come bound together. is it true that the harmonic functions occur because of the existence of holomorphic functions? So, theorem. Suppose mu is a harmonic function on G. Now, it turns out we need to have some conditions on G. That's fine. We're going to assume that G is just a very simple, nice region and that paths fit inside of it. There is some complexity that can be found if G doesn't have the right, if it's made in many pieces or, Look, we're just going to consider the simple case and not some idiosyncrasies. Then, there exists F, mapping complex to the complexes, holomorphic on G, such that F is equal to mu plus nu I. And the nu is the harmonic piece of F. Moreover, I'm sorry, just going to stop there. So, now how does this proof come into being? Well, first off, and a little aside here, is that we know something about mu of x. We know that these guys equal 0, and we also want them to believe that they came about because of F being holomorphic. That means if we write down mu of x plus the, well, we don't have the I, so if we rewrite the Cauchy-Riemann equations, then we can write minus I mu of y, that this, if we believe the answer, must be F prime. So why don't we just say let some function g be our mu of x, which we have in our hands, minus I mu of y, which we have in our hands. And now we have a very clear objective in mind. What we need to do is we need to show that F prime equals g. That's going to be really cool, because if we can show that, then we've proved exactly what we're looking for, that harmonic functions only occur as a consequence of the existence of holomorphic functions whose derivatives can demonstrate the harmonicity of the function. All right. All right, so the last thing I'm going to do here now is to successfully get that the function g is h prime, where h is some a plus bi. Now, in order to make this happen, we're going to calculate h prime as a sub x plus b sub xi. And if h is differentiable, its Cauchy-Riemann equations apply, and therefore I can write a sub x minus I a sub y. This is a reformulation of the Cauchy-Riemann equations. Now, what is g equal to? G is u sub x minus I u sub y. Now, if these two are equal, that says a sub x equals u sub x, which says that a then is u, up to a constant which may have a function of y here. So be it. But now we look at the other side, and we discover that a sub y is equal to mu sub y, which then a is equal to mu up to a constant function in y. Well, what's that mean? Well, there are only constant function that's a function of x, and a function of y is a constant. So therefore, this a in the h is actually mu plus a fixed constant. But wait a second. we've just succeeded. We have h, which has mu as a real part, and b sub I, if we throw that away, this thing's derivative is mu of x plus I b of x, which is our function g. And so we have a function that is differentiable that produces the mu sub x. And so we have a function f. That has what we want. That's kind of amazing. What does this mean? Well, this means that when we have a harmonic function, then we can actually find its harmonic conjugate and make a holomorphic function. So let's begin with that. Let's do an example of where a harmonic function comes from a holomorphic function by just stating the harmonic piece. So let mu of xy equal to xy. Let's check something about it. Mu of x is nothing more than the x derivative of this, which is y. Therefore, mu of xx is equal to 0. Mu of y is x. Therefore, mu of yy equals 0. Therefore, mu of xx plus mu of yy equals 0. So we have a harmonic function. That means it must be the consequence of somebody having had a holomorphic function. So then we're going to discover that holomorphic function. How do we do it? Well, we go back to that definition of g that we gave, which we want to be mu of x minus I mu of y. Well, in this case, mu of x is right here, it's y, and mu of y is x. And so we have our g. Now, what are we going to do with that? Well, we want to relate it to the nu, but it has to be nice because it says that it has to be related to derivatives. So I'm going to factor this minus I out, and I get x minus ix times x. Well, that must be a plus yi. It's the only way to get a plus y. Lo and behold, it must be iz. Well, that means we know what the function is that created that as a derivative. It has to be minus 1/2 I z squared. Then h prime of z equals our g. That's what happened. So that has to be the function that created this harmonic piece. So let's calculate it. So our claim function h of z is minus I over 2 z squared, which is minus I over 2 x plus yi squared, which is x squared plus 2xyi plus y squared with yi minus y squared. So minus I over 2x squared minus, so we're going to get a y squared minus x squared over 2I, and we're going to get a x, y, and lo and behold, our function h of z, which is xy plus y squared minus x squared over 2, is a holomorphic function where we have the nu in front. And why does this happen? It happens because h exists. It is the function whose harmonic fact has to occur because it's differentiable. This is really kind of cool. We can always write down the derivative and then solve for the other piece in every case.